The 1970s and 80s into the 80s were a dark time in radiation belt science. I remember the meeting rooms, the room closets that AGU put radiation belt sessions in. 4 of us there, Bill Imhoff, Bernie Blake, Martin Walt, and myself, talking to each other about radiation belt problems. And in the 1980s and 1985, there was a session organized by the history section of AGU that talked about the discovery of the magnetosphere. This is a picture of the invited speakers. This is Jim Dungy, Bob Helliwell, Carl McElwain, Alex Dessler, Shinaka Sofu here, and John Sprider, who is the co-convener. And I was there to provide sort of a more forward-looking view, I guess, future view. And there are a couple of things. One is that I was freakishly taller than the first generations of magnetospheric scientists. And secondly, I was proud that both in the remarks and in the published paper that I emphasized radiation belt science, and it had a lot of things left to learn about radiation belt physics, and I believe that's been borne out. The 1990s were somewhat better radiation belt science. The 1990-91 CRESS was launched, a very important mission. And in 1992, the SAMPEX mission, the Solar Anomalous Magnetospheric Particle Explorer, was launched, and it operated for the subsequent 20 years, and it was really quite an amazing mission. And of course, it was making measurements in low Earth orbit, but it was sampling all the different L shells. And I hope you guys like these kinds of L versus time plots, because I'm going to show a lot of them. But this really showed, or emphasized to me at least, how dynamic the radiation belts really are and how many sort of puzzling features there are. And that they're really driven by external processes and controlled by internal processes across an amazing range of scales. And probably one of the most revealing of the events really occurred in the Halloween storm. There was a hugely powerful coronal mass ejection, or several actually, that buffeted the magnetosphere, that completely changed the character of the radiation belts for an extended period of time, drove enhancement of the inner zone electron population tremendously. And this led to our Nature paper. It was a pleasure to work with Jim and Jerry Goldstein to be able to take the image data, to look at the EUV data that told us about the characteristics of the plasma sphere concurrently with the measurements of the radiation belt particle population. And of course, what it revealed was that the hottest particles, the most energetic particles in the system, are intimately related and controlled by the coldest plasmas and the waves supported in them, as Richard has talked about. And so this multi-scale phenomena and the degree to which the coldest plasmas play this surprising role for particles that are 10 orders or at least 8 orders of magnitude higher in energy really is quite fascinating. So the Van Allen probes were geared then toward addressing these kinds of questions in a much better way. With SAMPEX, despite my admiration for the program, it was pretty crude in many ways. Very limited energy resolution, not a very comprehensive look at the particle populations by any means. Waves were absent, and so on. So the Van Allen probes program was put together to provide essentially all that we might want to have as far as the properties of the plasmas, waves, fields. This is the spacecraft that you've heard about some of these things before, the electric fields and waves, the magnetic fields and waves from emphasis, and the ring current particle populations from Lu, and ultra-relativistic inner zone protons from Joe Mazer and company. And then the suite that measured the plasmas and energetic particles. I'm going to talk to you about the REP instrument. I'm very proud of this instrument and the engineers at LASP that built this with us. It was geared toward measuring the relativistic, super-relativistic particles in ways that had not been done before. Von Hoxie, Susan Batiste, the instrument scientist, Sri Conical. We worked very hard to find the best, fastest detectors, to use well-conceived shielding, to design an operational strategy that would really allow us to suppress Bremsstrahlung background, to avoid chance coincidence detectors, to have other kind of backgrounds suppressed. And it really has worked surprisingly well. We also realized that we had to have a high precision, high accuracy in the measurements. If we imagine at relatively high energies here, the kind of radial gradient that we might expect, then if we're going to distinguish the radial diffusion kind of acceleration, we would have to have an ability then to distinguish that clearly from the kind of local heating that Richard was talking about. And if we had large uncertainties, but common in these kinds of measurements of 30%, it starts to get a little dicey. Larger uncertainties completely washes out the effects. And so we really expended considerable effort to try to get good accuracy between the instruments and within the energy range. America's greatest philosopher, Yogi Berra, said you can observe a lot just by looking, and that has been borne out here. We were supposed to turn on the REPT instrument in about 35 or 40 days after launch. Because SAMPEX was expected to be coming to an end to re-enter the atmosphere, I guess I insisted that we turn on our instrument much sooner, 3 days, not 3 weeks or 3 months after launch in the commissioning phase, and I'm delighted we did. As Richard was pointing out, we turned on right in the heart of in the midst of a high relativistic acceleration event. Again, for the format L versus time here, this is overplotting the instrument on the A spacecraft with the B spacecraft, and so it gives this kind of complete swath of observation. You can see the striations there. And this is 4 to 5 MeV electrons, looking in a place with SAMPEX that we'd never really resolved well before. But then the two-belt structure is quite evident. Then along came a strong interplanetary shock, wiped out much of the outer zone, but not all of it. And then this long period that Richard mentioned as well. My first thought was, geez, there's something wrong with the instrument. This isn't supposed to be the way it is. They always said there were 2 belts, not 3. But I guess Sir Arthur Eddington remarked that he refused to believe an observation until it was confirmed by theory. So we started talking with Richard, and we understood that this not only is possible, but maybe could even be an expected thing. So what we see played out here is the inner zone, the slot region, this storage ring feature, as we dubbed it, and the highly variable outer zone. And so I'm going to show you just this playing out now, the observations. That what you'll see on here below will be orbits laid on top of one another. So it's a magnetic latitude kind of projection. And so this will show that we started out with a 2-belt structure. This storage ring features there. It just stays there and stays there, gradually decaying. But then the outer zone is really out there varying as it will. And then along comes a very powerful interplanetary event. Things get cut off like a knife edge almost. Further reduction, and then the strong acceleration event that occurred in October that, again, Richard talked to you about. So this really played out. This was showing us features, at least that I thought we never could really see, or probably wouldn't see, but we were seeing these all in the first month or so of the spacecraft mission. So here's the kind of picture of all of these different features we're sort of identifying in the data, and very nice. So this is Andy Kale's nice illustration that appeared in Science of the 3-belt structure, the inner zone, the slot, the sort of expected slot, this 3rd belt or storage ring that's in there. And the Van Allen probes were perfectly geared toward observing observing these kinds of things. The other thing, of course, we have here is ample information about what the external drivers are from ACE and other such things. So we have the speed, the magnetic field properties, the geomagnetic condition under which this occurs. But very, very important is that we have the direct measurements on the Van Allen probes of the plasma properties, and so we know where the plasma sphere is. And again, what we see is that the acceleration events occur when the plasma sphere is compressed far in. As it recedes and moves it back out to a more normal location, then these features that have been produced can just stay there for the long kinds of periods that Richard talked about, gradually being lost by Hiss. But if a strong enough event comes along, it can completely eradicate or nearly completely eradicate. And what has amazed me again is how quickly you can eradicate a population and how quickly you can regenerate it. So this was the idea. This is a better picture than I showed you before, more a 3D picture from Mike Henderson for the Reeves et al. Paper, taking this October event and trying to contrast the sort of two competing pictures, the gradualism of radial diffusion, the abruptness of local acceleration deep inside the system. And what I love looking at the data in these blown up versions of the L versus time plots. And just this is, again, 4 to 5 MeV. And the Rep-A spacecraft looping out and in, the Rep-B. There's nothing there beforehand. Bang, we come through and we see on both spacecraft the appearance by a couple of orders of magnitude increase in flux. So that's really the anatomy of particle acceleration, and it's an extraordinarily efficient and effective accelerator. And Richard again showed this picture from the Reeves et al. Paper then that you can always argue, well, you're missing things when you're looking at flux. You really have to convert to phase-space density to take account of magnetic field changes, and so we've been able to do that beautifully on the Van Allen probes. And so before the event, we see the paucity of particles, and then the buildup deep inside, not outside, not coming from outside, but building up locally right in the middle here. And I think of Margaret's work with Janet Green, the difficulty of getting those measurements from polar. Here we've got it nailed, I think. It's a beautiful illustration. So I like to look at these L versus time plots over long periods. I think they're very artistic, among other things. But here's like from the turn on to the end of November. And as you look at the 2 MeV, the region of energy space that we're so familiar with, you see just how active it is. But as you go to higher and higher energies, up here we're 5, 6, 7 MeV, the events become much more rare and much more spectacular in my mind. The fact that we're seeing 7, 8, 9, 10 MeV particles accelerated in these abrupt ways is quite exciting. But also the gradualism of the system. Stephen J. Gould talk about punctuated equilibria, and I think that's sort of what the radiation belts characterize, that you have powerful events like the October 2012, and then there can be long periods, months, where the system is simply relaxing, gradually relaxing back to its base state. And so Von Hoxie, the instrument engineer, remarked on, well, we can take this period in like November and December where things are just gradually changing, and how about if we put it in a geographic view? So instead of using the usual local time or something, just fix the Earth, and the orbits then spiral around, and eventually in that month and a half they cover the entire longitude. And so this is like the spirograph toys we used to play with, plotting out, showing the inner zone, the slot region, and after the 3-belt structure had gone away, so now we just get this outer belt portrayed right before our eyes, and this was some of the kinds of plots we showed in the recent EOS article about Van Allen probes. So the first year, for those who are more colorblind, more color challenged, this is Allison Jane's preferred color bar. She's not colorblind, but she's sensitive to others who are, I guess, and I hope this shows some of the features too. And this is from our recent GRL paper that's just been published. And you're seeing the same things I was showing you before. This is the 2-ish MeV extending up to the 8, 9, 10 MeV. And again, what's remarkable, of course, was that this October event produced particles up to such very high energy, and then we can watch them sort of decay away. But I'm going to draw your attention to this March 2013 period, quite a fascinating interval, as I hope I'll show you now. But also recognizing that as you look at the data here, you can see that the 3-belt property is not that rare a thing. It's something that occurs rather naturally, where you have persistence of some previous feature, and then a new kind of episode of solar wind driving occurs. And in many ways, the radiation belts have the thumbprint of every indignity that the magnetosphere has suffered in its recent history. They're all kind of there, gradually changing and evolving away from what happened previously. So this March period is really quite neat, I think. And it is neat because at the beginning of the period, the intensity of particles across the energy range is generally pretty low. But you've got the persistent effect of the 3 to 3.5. The storage ring is back there, and you can see it. This is superimposed on here is the plasma pause location, again illustrating the kinds of things that I tried to talk about and Richard talked about too, that you change things, you compress the magnetosphere, erode the plasma sphere, and the acceleration can occur. You then relax back, and the system evolves away from that, or gradually changes from that state. And I think this is a beautiful textbook kind of case of inward radial diffusion. You can just watch it before your eyes there. And then there's a very powerful shock wave that comes along and wipes out the radiation belt across essentially all the energies pretty completely. And then there's a rapid resurgence, and again extending up to of order 7 or 8 MeV. So we can get exquisite views of the dropout and recovery process with the Van Allen probes. Again, this is 2 to 3 MeV kind of particles. There's no place for the particles to hide with the Van Allen probes. With SAMPEX, you could argue, well, you're down at low altitude, you're not really seeing the entire distribution. Here we're right at the equator, we're seeing everything, and they're gone. They're essentially completely gone, and then they come back, and they come back right in the middle of the system. So it's not radial diffusion. The pitch angle distribution information is also wonderful on the mission. And for the shock that arrives at 0604 UT, I don't know how well you can see it from back there, but you can see that it's the 90-degree particles that are wiped out. Part of the distribution is really being lost through the magnetopause very clearly. That's what's eroding them away, and they're going away. And when they come back, they're coming back at 90-degree pitch angles. So it's you've got sort of everything you want to know. You've got the waves, you've got the fields, you've got the pitch angle information to really piece together how the whole thing worked. And it's been a delight to work with John Foster, Phil Erickson, and others on this particular event on the 17th of March. To be able to see the chorus emissions that occur in conjunction with a very strong substorm onset at 22:15 or so. And at that time, the lower energy particles are strongly injected. The chorus emissions are strongly enhanced. And lo and behold, we see in a time scale of, from one pass through to the next, which limits it to a few tens of minutes, that the phase-space density of relativistic electrons, 4, 5, 6 MeV, go up by 2 or 3 orders of magnitude. So this accelerator, associated clearly with the chorus kind of acceleration Rich is talking about, is not a slow thing, it's a fast thing, and it can be faster than at least, again, I ever expected we could really see, and we've got the goods on that from these kind of measurements. Again, John talked about the much broader context, the convection, the ionospheric effects, the whole deal. And I believe that we're really seeing how intimately coupled the entire system, the solar wind, the ionosphere, the magnetosphere, everything is connected to everything else, and it's all playing its role in this efficient cosmic accelerator. So this is probably my favorite figure from the GRL paper, because it shows the phase space density. These would be about 1 MeV-ish particles at geostationary orbit at the start. These would be like 1.5, and by the time they get into 3 or 4, they're 7 or 8 MeV particles. These are cuts that are taken at every 0.2 of an L. I don't know how well you can see it from back there, but from 3.8 to 5. And and this is, again, the solar wind driver information. And so this is the first event I was talking about, beginning early March, is driven by high-speed solar wind stream. The second one is driven very differently by coronal mass ejection. And if you look at these, now you see this is the picture of what radial diffusion looks like. You start out with relatively high densities, phase-space densities out at higher L, and you can watch that population radially diffuse in and energize as it goes in. Tremendous contrast with the signature of local acceleration. Here everything jumps up, it's very abrupt, and the entire population at all L's is relevant L's is essentially enhanced at the same time. So conclusions, I think the results from the radiation belt storm probes, the Van Allen probes, have already begun to rewrite the textbooks about acceleration, transport, and loss. I think the probes join with the broader solar observing and near-Earth platforms, and here I emphasize not only space platforms, but ground-based systems, to allow us to make clear Sun-Earth connections that were not really possible previously. I'm very proud of the rep that clearly shows there are extended periods of gradual changes in these mildly to super relativistic electron populations that are punctuated by these remarkable losses and rapid acceleration. And I think the comprehensive packages that we have there are providing sort of undreamt of views of the radiation belt processes. I have new windows on the first discovery of the space age. So I'll let this play while we take questions, but these really join a unique constellation of spacecraft. We better do it now. We'll never have a better chance to study these things. Thanks.
Questions to Dan? Yes, Vanya.
I have a question about the storage ring. So how often have you observed this, and is this a regular feature of the radiation belts now we should expect?
The 3-ring?
Yeah.
Yeah. Well, I think we should expect it fairly commonly. When the conditions are right, if you've not eliminated the previously produced population or only partially eliminated the outer zone, then this population is there. If the plasma pause retreats out to its more normal location, then it's only the weak His interaction that Richard was talking about that leads to its demise. And so the first one we saw was bookended by two things. One was a fairly strong coronal mass ejection that wiped out part but not all of the outer belt. It ended with the annihilation of essentially the entire outer zone. So whenever those conditions are met, I would expect that we'll see 3-ring. In fact, if you look carefully at some of the plots I showed, we're actually seeing 4 rings. There's a famous movie called The Freshman with Marlon Brando and Maximilian Schell. Maximilian Schell says, "Carmine told me there would be 1 boy, and here there are 2." And so I always think of him saying, Van Allen told us there'd be 2 belts, and here there are 3. So I don't know. We'll have to see how far it goes.
Okay, Richard?
Is that on? Yeah. I just wanted to let you know, Dan, that we've now done a simulation of other storms, and in particular the March 17 storm, and we come up with essentially the same conclusion. You can get this very rapid acceleration, and we get a pretty good agreement. I also wanted to point out to people that if you actually try to do the phase space density analysis at lower magnetic moment, and Drew Turner has done this, he shows that you do get this very gradual monotonic increase as you go into the outer radiation belts at low magnetic moments, and that shows that the seed population is being convected or diffused into the system. It's only when you get above about 500 MeV per Gauss that you start to see these peaks in phase-space density developing.
October seems to be a good time. There are other shocks that, like October 2013, has produced some beautiful enhancements too. So we got a lot of things to do.
I have a question on your plots with the very long-term inward radial diffusion.
Right.
Is anybody looking at that and looking at the diffusion rates and looking at the field fluctuations and all to go back to the classic radial diffusion calculations and determinations? Because it's such a beautiful set of data. That's the kind of thing that we were looking at back in the 60s and 70s, and nothing like this existed.
Right. Well, I think Richard is. I think Allison Janes, who's a postdoc with us, is looking at the quiet periods, the gradualism part of the talk here.
I think that's really very important also
too.
in terms of
Yeah.
radial
No,
diffusion.
the system will never be closer to its ground state, and sort of watch it just evolve away from that. Oh, and then the next speaker. Yes.
Okay.
I was remiss in not pointing to the next speaker.
Other
May I ask a
questions?
question? Yeah.
Pardon?
May I ask a question?
Yeah, Rich.
Dan, I wondered if you were able to try to trace the heritage of the electrons that end up being accelerated to make the outer zone. Would they have come from the plasma sheet? How would they have found their energy as they?
Yeah. Well, for example, the 2nd of March case clearly was a substorm population at the at the time of the high-speed stream, and so those are clearly plasma sheet particles, probably up to a couple hundred kilovolts. Working with the Mag Ice team, we see that forms the seed population, which then begins to be processed by these other things. Very similarly, the shock-accelerated ones are also. It's so wonderful to be able to look from a few EV, on up to multiple, like 10, 12 MeV. You can just see that you've got the cold plasma, you've got the hot plasma, you've got the seed population energized by substorms playing a key role, and then you've got the processes that take over that I've been talking about, Richard's talking about, that really process that population, and so we've got played out before us all of the sequence of things from the coldest, as I said, to the hottest, and it's not that we have to just look at one end or the other. The entire spectrum is there for us to see.
Thank you.
Okay, time for one other question? If not, thanks again, Dan.
Thank you.